Hello, my name is Alex and I'm here to help. Today I'm going to help you derive the equations of motion that are commonly used in physics. And these are all assuming constant acceleration. Acceleration can equal zero, but it cannot change. Okay, there are three important things that need to be brought up before we can get to the equations. And they are position, velocity, and acceleration. Position is basically just a measurement from point A to point B, and it can be calculated like this. Here's an example. He drove 75 miles away from home. That just means his position 75 miles away relative to his home. And it's just a measurement. In this case, if you do the unit conversion, it's 120.7 kilometers. Velocity is the change in position over time. If you want to figure out how long it takes to go somewhere and you know the distance, you can calculate the average velocity. And here's an example. He ran 100 meters in 9.58 seconds. The velocity equals 100 meters divided by 9.58 seconds. And that equals 10.438 meters per second. If you want to calculate how long it takes velocity to change over time, this is known as acceleration. And here's an example. A car can go from 0 miles per hour to 60 miles per hour in 2.2 seconds. The acceleration is equal to 60 miles per hour divided by 2.2 seconds. Doing the unit conversion and the proper calculation equals 12.192 meters per second squared. Once you get the final definitions down, then you can work on deriving the equations. And I'm going to work backwards, starting with acceleration. At first, I'm going to do this using no calculus. Later, I'll get to the calculus derivation. Acceleration is defined as the change in velocity over the change in time. In equation form, that looks like this. A equals delta V over delta T. This delta sign means change. V minus V initial, T minus T initial. Typically, T initial equals 0. We usually start from T equals 0 in most problems, unless otherwise stated. So, given that, AT, bring the T over to the A, equals V minus V initial. And this can be rewritten to our first major equation, V equals V initial plus A times T. If you know the initial velocity, and you know acceleration, and you know time, you can calculate V. Next, you move on to the definition of velocity. Change in position over change in time. The average velocity can be calculated as the total distance traveled over the time it took to go that distance. And if you also remember how you find the average of two numbers, one number plus another number divided by 2. Average velocity, final velocity, plus initial velocity divided by 2. From here, you can get the second major equation. Distance traveled equals the average velocity over multiplied by the time it takes. Third equation can be derived by combining the first and second. If you take that first equation, this one here, and you plug it in to this V right here, you get delta x, average velocity times time, and then you plug in the first equation to right here from here. Combining terms, it can be simplified to our third major equation. If T initial equals 0, delta x equals V initial times time plus 1/2 A T squared. There's a third equation that can be derived. It's known as the time-independent equation. If you don't know time, you have other equations at your disposal. You have the third equation and the first equation. First equation can be rewritten to solve for time. T equals V minus V initial over A. If you plug this into this equation, you get this. Whoops. Delta x equals v naught times that big guy, 1/2 a times that big guy again, squared. It looks a little messy, but when you do the manipulation and you simplify, you get this. This is the form that it's typically written in. V squared equals v initial squared plus 2a delta x. And this is known as the time-independent equation, because there is no time part to it. So if you know the initial velocity and acceleration and position, you can calculate final velocity without even knowing how long it took. These are the four major equations that are used in kinematics. And I derived them without calculus. It's possible to do it with calculus, and I'm going to show you that now. Acceleration is defined as the derivative of velocity with respect to time. Rewriting this, you can get a dt equals dv. Integrating both sides, you get a dt from 0 to t, dv from vi to v equals at equals v minus v initial. Rewriting for v, and you get the first major equation, v equals vi plus at. And it's the same as this one over here. Then next, moving to velocity, we know that velocity is defined as the derivative of position with respect to time. Change in position over change in time. Rewriting this, dx equals v dt, and plugging the first equation, plugging this into here, we get vi plus at, the sum of that times dt. Then, integrating both sides, we get 1 dx from xi to x equals vi plus at dt from 0 to t. Integrating and simplifying, we get our other major equation. Change of position equals vi times t plus 1/2 at squared. The time-independent equation can be derived using calculus as well. Going from the definitions of acceleration and velocity, they can both be rewritten to solve for dt. dt equals dv over a equals dx over v. Using these second two fractions here, you have a dx equals v dv. Integrating both sides from xi to x and vi to v. Integrate, simplify. Whoop, doesn't fit there. You have x minus xi times a equals v squared minus v initial squared over 2. Rewriting, this is the way it's commonly written. V squared equals v initial squared plus 2a delta x. Okay, so those are the three equations. What's very important to realize is that these, the three components we have, position, velocity, and acceleration, are all vectors, which means they have an x, a y, and a z component. You won't always see a z component, but technically it's there. Usually it's just 0. But if things are moving in 3 dimensions, you have to worry about the z. So, given the three equations, you have to be mindful when you talk about velocity, position, acceleration that you specify which component you mean. Notice the subscripts, v final x, v initial x, a x. You have to do that for the y direction and the z direction. You have v initial y, ay, delta y, v initial z, az, delta z. Vectors have components. Very important. This set of equations will govern pretty much all of the motion in physics, assuming constant acceleration. If you have a problem that you're struggling with, send it over to me. alexpleasehelp.com.